Good day, class. For this video, we're going to talk about area, and not just any kind of plane figure area. Our topic is about the area of regular polygons. For those who have taken their geometry course, in finding the regular polygon's area, they'd recall this formula, 1/2 AP, where A is the apothem and P is the perimeter of the polygon. Sadly, teachers rarely give us a worthy intuition on why this formula works. I've personally seen videos where they draw line segments on a polygon, but I think we can make the representations better and clearer today. This video will show you a full animated intuition, or depending on how you think of it, a graphically aided derivation of this formula. However, this video doesn't end here. For the past few weeks, I have been completing this paper for our investigation class, and I have discovered something no Google or other search engine has shown me before. We have another formula for the regular polygon's area, which is based in trigonometry, and I was able to model a pretty accurate algebraic substitute which we can use to compute this area by hand. No more calculators. If you somehow have this inner hate on trigonometry like I do, this video is for you, so stay tuned till the end. Now before everything else, let's begin with the simplest regular polygon we can think of, the equilateral triangle. As we've learned from as early as elementary mathematics, we all know that the formula for a triangle's area is denoted by 1/2 BH, where B refers to the figure's base and H refers to its height, or altitude in some references. In short, we don't have a problem computing for the equilateral triangle's area. For n, or side length of 4, we have the square. The square has a far simpler formula to the point that its formula is named after itself. Just square the length of its side. No need to elaborate this one. But starting with n of 5, or the regular pentagon, we can observe that we don't have a straightforward approach in computing for its area anymore. In fact, it gets more problematic when we look for the area of an irregular pentagon, though it is outside the scope of this video. So how do we compute for its area then? As I have mentioned earlier, the formula we use is 1/2 AP, where A is that segment they call the apothem and the P is the perimeter of the regular polygon. They say it works with all regular polygons, but how? I'll give you a hint, and it goes back to the area of a triangle. Here we can see a regular pentagon. Did you know that you can divide a regular pentagon into 5 triangles? And not just 5 random triangles, we're talking about 5 congruent triangles. They're not necessarily regular like the equilateral triangle we've seen earlier, but these triangles can indeed lead us to something. In addition, this characteristic not only applies to the regular pentagon. For any regular n-gon, we can divide it into n number of triangles. This trait exists on any regular polygon, even on the equilateral triangle and the square, though they're not as useful. Here's a hexagon. Let's draw line segments from the center to divide it into 6 triangles as shown here. Now we're certain that they're congruent because they overlap with one another. Hence, what we can observe from one triangle would be very likely the same for all other triangles. Let's pick one triangle. Recalling what we've talked about earlier, given the base and height, we have the formula 1/2 BH. Here is where it gets interesting. When we reconstruct the hexagon, we can see that the triangle's base is the same as the side length of the hexagon. Now we have this line segment extending from the center, perpendicular to this side, which has a length equal to the height of this triangle. This segment is called the apothem, from the Greek word apothema, which means deposit, which I think doesn't make sense with the context, but hey, at least it deposits some cool information about the regular polygon. Okay, I'm not going to argue further. So this 1/2 base times height can be replaced by 1/2 side length times apothem, which is denoted by the formula 1/2 SA. Since there are 6 triangles with these same dimensions, all we need is to multiply what we've got by n, or the number of sides. 1/2 SA times n can be further simplified by swapping the places of S and A. It works. and we don't violate any rules because of the commutative property of multiplication. And now, we can replace the groupings so S and N can go together. Again, we just apply the associative property here. We all know that the length of a regular polygon's side times its number of sides result to its perimeter. Hence, the very formula we all know is 1/2 AP, where A is the apothem and P is the perimeter of the regular polygon. Now I've mentioned earlier that there is another formula in finding its area, and it's based on trigonometry. The formula is this: 1/4 S squared cotangent 180 over N, where S is the length of one side and N is the number of sides implied by the polygon's name. How do we come up with this one? Surprisingly, it originates from the first formula we've tackled earlier. I even managed to derive it myself. Here's what I did. First, I let P be equal to Sn, where S is the side length and N is the number of sides. In other words, I'm going to bring back the quantity side length and the number of sides, since they will be useful for these following steps. Next, we'll compute for the apothem in terms of both S and N. We will establish the foundation on the fact that the apothem is the altitude length of each triangle we've seen earlier. We can find the value of this angle indicated in blue, given only the number of sides n of a regular polygon. Then, by using trigonometric functions, we can compute for the apothem using this angle in yellow, which is half of the polygon's interior angle, and also half of the base of the triangle, which represents the side length S of the entire polygon. Let's recall the formula for the sum of interior angles of an n-gon as n minus 2 times 180, wherein each interior angle would be n minus 2 times 180 all over n. Then the half of each angle would be n minus 2 180 all over 2n. Distribute 180 to the quantity and simplify with the denominator, and we get 90 minus 180 over n for the half of each angle. Now that we obtain this angle, let's introduce the tangent function in the figure, as tangent theta is equal to the opposite side, which is the apothem, divided by the adjacent side represented by the half of the side length. We get this expression. Multiply both sides by 1/2 s, equate tangent of 90 minus x to cotangent x, and then we get 1/2 s cotangent of 180 over n. We're almost there. Combine this with the other variables of the original formula following the commutative and associative rules, and we finally get 1/4 s squared cotangent 180 over n. Just plug the values of s and n, and we get the area by pressing the right buttons on a calculator. But what if we don't have a calculator? Maybe calculators are not allowed during situations like exams, or worse, we don't have physical access to one of these devices. What do we do now as math educators? This was the topic of my investigation paper linked in the description. In this second half of this video, I will show you how I've constructed an alternative formula that is pretty accurate and is based on algebra, and therefore is easy to compute by hand. I've used Excel and the formula we got earlier to encode the areas from the equilateral triangle up to the 1000 gon from side lengths 1 to 3 units. Then, applying a little bit of linear algebra, I've come up with varying formulas for each side length. For side length of 1, we have this function 0.0795712 n squared plus 0.0002843 n minus 0.265418. For side length of 2, we have 0.3183142857143 n squared plus 0.0002285714286 n minus 1.05471428574143. And for side length of 3, we have 0.716141 n squared plus 0.002552 n minus 2.388706. Whew, that's a lot of numbers. By the way, this is how they look when we compare their graphs to the original. If we compare the three leading coefficients though, we can see that the second is about 4 times the first, and the third is 9 times the first. Now I was able to obtain a more general expression. S squared multiply this quantity of 0.0795712 n squared plus 0.0002843 n minus 0.265418. I believe this needs more work, so I did my best to round off and factor as much as I could without compromising accuracy. Fast forward and now we've got this new formula. 0.0796 s squared times the quantity n plus 1.83 times the quantity n minus 1.82. I don't want to act like everyone should believe me outright without proof, do I? So, we'll solve a few problems using this formula here instead to see how it holds up. Problem number 1. Find the area of a regular pentagon with a side length of 25 centimeters. Using the original formula, let's replace n with 5 and s with 25. We don't have much else to write here. Just replace cotangent 180 over 5 with perhaps 1 over tangent 180 over 5, as most calculators only have the sine, cosine, and tangent functions. The answer appears to be 1075.298. Now using my own formula, plug the same n and s values, and we get 1080.54. This, depending on the field you are working on, is good enough, especially if you are using this just to give your students a way to estimate the polygon's area without a calculator. Let's try another problem. Find the area of a regular octagon with a side length of 10 inches. Again, using the original formula, substitute 8 for n and 10 for s. Then, press this equation into your calculator and you would get the answer 482.843. Using my own formula and substituting the values, we can compute this one on paper, albeit a long but not a difficult process. The output for my own formula is 483.565. A mere difference of less than 1 unit it is. As we can observe, it gets pretty accurate enough even if we don't use trigonometric functions our handy calculators have. Here is a table comparing the ratio between the error from the original formula and area for all 3 side lengths. I have observed that my own formula tends to output a little higher than the original, but with an error of less than 1% for a pentagon onwards. Given the fact that we can solve this one without calculators, we don't have much to complain about here. It is true that this topic requires further investigation, but hey, maybe in the future we can develop more new and refined math strategies that can be of great help to our students. That's all for this video and thank you for watching.